When human beings first tried to understand light, they did not begin with equations, experiments, or instruments. They began with direct experience. Light was something that allowed vision, created shadows, revealed shapes, and disappeared when night arrived. It seemed to travel instantly, always in straight lines, and it behaved with a consistency that felt almost self-evident. These everyday observations formed the foundation of the earliest ideas about light, long before science existed as a formal discipline. In ancient civilizations, light was often explained through philosophy rather than experimentation. The Greeks were among the first to seriously question how vision worked and what role light played in it. Some philosophers believed that vision occurred because the eyes emitted rays that touched objects, making them visible. Others believed the opposite, that light traveled from objects into the eyes. Although these ideas were speculative, they already introduced a powerful concept: light moves in straight paths, which could be imagined as invisible lines or rays connecting the eye and the object. Euclid, around 300 BCE, treated light geometrically. He did not attempt to define what light was made of. Instead, he described how it behaved. By assuming that light traveled in straight lines, he was able to explain reflection from mirrors using simple geometry. Angles could be measured, paths could be drawn, and predictions could be made. This approach was incredibly successful because it matched what people observed. Shadows had sharp edges, mirrors reflected images predictably, and light appeared to move in straight paths unless something interfered with it. These straight-line assumptions became deeply ingrained and remained influential for thousands of years. Aristotle offered a different perspective. He rejected the idea of light as something material traveling from place to place. Instead, he described light as a quality of a transparent medium, something that existed when the medium was activated by a luminous source. In his view, light did not travel through space as an object or substance. It appeared instantly when conditions were right. While this idea avoided the problem of explaining extremely fast motion, it struggled to account for shadows, reflection, and directional behavior. As a result, Aristotle's view was less useful for practical optical explanations, even though his authority dominated natural philosophy for centuries. As knowledge passed through the Islamic Golden Age, scholars such as Ibn al-Haytham made critical advances. He firmly rejected the idea that vision came from rays emitted by the eye and argued, instead, that light traveled from luminous sources to objects and then into the eyes. Through careful reasoning and experimentation, he demonstrated that light moved in straight lines and could be blocked, reflected, or refracted. His work emphasized that light behaved like something that traveled, even if its exact nature was unknown. This reinforced the ray concept and laid the groundwork for later scientific models. By the time of the Renaissance and early modern science, the ray model of light had become firmly established. Artists used it to develop linear perspective. Engineers used it to design lenses. Astronomers used it to build telescopes. Light rays were not considered physical objects in the modern sense, but they were treated as paths along which something traveled. This something did not yet have a clear identity, but its behavior was predictable enough to be useful. The question of whether light was a wave or a particle emerged most strongly in the 17th century. This period marked a shift from purely descriptive models to attempts at explaining the underlying nature of light. René Descartes suggested that light was a pressure transmitted through a subtle medium filling space. In his view, light behaved somewhat like a mechanical disturbance, pushing instantly through matter. This idea preserved straight-line motion while avoiding the need for light to be composed of tiny moving objects. However, it lacked experimental support and could not easily explain certain optical effects. Isaac Newton approached the problem with a different mindset. Influenced by his success in mechanics, he believed nature could be understood through particles obeying forces. He proposed that light consisted of extremely small particles emitted by luminous objects. These particles traveled at high speed in straight lines, which naturally explained shadows and sharp reflections. When light struck a mirror, the particles bounced off, just as balls bounce off a wall. When light entered a denser medium like glass or water, Newton proposed that attractive forces pulled the particles inward, causing refraction. Newton's particle theory of light, often called the corpuscular theory, was powerful because it fit neatly into his broader framework of physics. He could explain reflection, refraction, and the straight-line propagation of light using the same principles that governed motion. His authority as a scientist also played a significant role in the acceptance of this model. For many decades, Newton's view dominated scientific thinking, especially in England. The particle view of light also aligned with common sense. People were already familiar with projectiles, collisions, and straight-line motion. Imagining light as a stream of tiny, fast-moving particles felt natural. It also explained why light appeared to travel in straight lines, and why it could be blocked completely by opaque objects. Darkness seemed to result simply from the absence of these particles. However, even in Newton's time, there were signs that the particle model was incomplete. Newton himself observed phenomena that were difficult to reconcile with simple particle behavior. His experiments with prisms revealed that white light could be separated into colors, each bending by a different amount. While he explained this by assigning different properties to particles of different colors, the explanation felt descriptive rather than deeply causal. Meanwhile, proponents of wave-like ideas continued to challenge the particle model. Christian Huygens argued that light behaved more like a wave spreading through space. While this wave theory would later gain strong experimental support, at this early stage the debate was not yet settled. Still, the persistence of straight-line motion in light kept ray and particle models at the center of explanation. What is crucial to understand about these early ideas is that ray and particle were not mutually exclusive concepts in the way we think of them today. Rays were often used as mathematical tools rather than physical claims. A ray represented the direction of light's travel, not necessarily a material object. Particles, on the other hand, were attempts to give light a physical substance, something that could interact mechanically with matter. The ray concept was especially valuable because it allowed scientists to ignore questions about the internal structure of light and focus purely on geometry. Using rays, one could calculate image positions, focal lengths, and angles without knowing anything about what light truly was. This practical success made the ray model indispensable, even when deeper theories evolved. At the same time, particle ideas reflected a growing desire to unify natural phenomena under a single mechanical framework. If planets, stones, and gases could all be understood as particles in motion, why not light? This ambition drove much of early modern physics. Light, in this view, was not mysterious or special. It was simply another form of matter behaving according to universal laws. These early particle ideas also shaped how scientists thought about energy and interaction. Light was assumed to carry momentum, exert pressure, and transfer force upon impact. While these assumptions were speculative, they foreshadowed concepts that would later reappear in more refined forms. Yet, despite their strengths, early particle models faced conceptual challenges. If light consisted of particles, why did particles not collide with each other? How could multiple beams of light cross paths without interference? Why did light sometimes produce patterns that suggested spreading and overlap rather than simple trajectories? These questions did not immediately overthrow the particle view, but they lingered as unresolved puzzles. Before quantum theory, these tensions remained largely hidden beneath the success of ray optics and classical explanations. Scientists were content to use whichever model worked best for a given problem. Rays were used for geometry, particles for interaction, and deeper questions were often set aside. The early history of light, therefore, is not a story of ignorance, but of gradual refinement. Rays and particles were not wrong ideas, they were incomplete ones. They captured important aspects of light's behavior using the intellectual tools available at the time. They reflected how humans naturally try to understand the world by extending familiar concepts, by trusting observation, and by building models that work even if they are not final. This early phase set the stage for everything that followed. By treating light as something that travels, whether as rays or particles, scientists established the idea that light has direction, speed, and interaction. These assumptions would later be challenged, revised, and expanded, but they never disappeared. Even today, rays are still drawn in optics textbooks, and particles reappear as photons in quantum theory. Understanding how light was viewed before quantum theory is not just about outdated ideas. It reveals how scientific thinking evolves, how models can be useful without being complete, and how intuition guides discovery long before deeper truths emerge. The ray and particle views were humanity's first serious attempts to grasp the nature of light, and they shaped centuries of scientific progress. As these early ideas matured, they began to influence not only science, but also how people understood reality itself. Light was no longer just a practical tool for seeing, it became a bridge between the physical world and human perception. Philosophers debated whether light belonged more to the object being seen, the space between, or the mind that perceived it. This philosophical tension shaped scientific explanations in subtle but powerful ways. One of the most important assumptions embedded in early thinking was that light behaved predictably and deterministically. If light traveled as rays or particles, then its path could, in principle, always be traced. There was comfort in this idea. It meant the universe was orderly, governed by clear rules, and fully accessible to human reason. Before quantum theory, uncertainty was not considered a fundamental feature of nature, but rather a limitation of measurement or knowledge. This deterministic mindset reinforced the dominance of straight line motion as the defining feature of light. Straight lines were simple, measurable, and mathematically elegant. They aligned with Euclidean geometry, which was seen as a universal truth. When light bent or reflected, it did so according to precise angles that could be calculated and predicted. This reinforced the belief that light followed strict laws, similar to those governing solid objects. As optical instruments improved, these ideas were tested in increasingly sophisticated ways. Lenses magnified distant stars and tiny organisms, yet the basic ray picture still held. Light entered a lens, bent at the surface, traveled through the material, and bent again as it exited. Everything about this process could be described using rays and angles. The success of these instruments strengthened confidence in classical explanations and delayed the need for deeper theoretical revisions. The development of microscopes and telescopes also raised new questions. When observing very small or very distant objects, light sometimes behaved in ways that strained the ray model. Images blurred, fringes appeared, and resolution limits became evident. At the time, these effects were often attributed to imperfections in instruments rather than to light itself. The assumption remained that light fundamentally traveled as straight rays, and any deviations were secondary complications. The particle interpretation continued to evolve alongside these practical developments. Light particles were assumed to be incredibly small and fast, far beyond direct detection. Their invisibility was not seen as a weakness but as a natural consequence of their size. After all, atoms themselves were hypothetical for much of history. The idea that unseen particles could produce visible effects fit comfortably within the emerging atomic worldview. This particle-based thinking influenced how scientists understood color, brightness, and intensity. Brighter light was assumed to contain more particles, while dim light contained fewer. Different colors were associated with different particle properties, such as size or speed. These explanations were not experimentally precise, but they provided a coherent narrative that connected perception to physical causes. At the same time, the ray concept remained neutral regarding the substance of light. It did not care whether light was made of particles, waves, or something else entirely. Rays were tools of description, not claims about reality. This flexibility allowed ray optics to survive even as debates about the true nature of light intensified. It also meant that many scientists could work productively without committing to a specific ontological position. This separation between practical models and deeper explanations became a defining feature of pre-quantum physics. A theory was judged primarily by whether it worked, not whether it revealed ultimate truth. This pragmatic attitude allowed classical optics to flourish even as conceptual tensions accumulated beneath the surface. Cultural and technological contexts also played a role. The rise of navigation, astronomy, and engineering created a strong demand for accurate optical predictions. Sailors relied on sextants, astronomers on telescopes, and architects on perspective. These applications did not require a complete understanding of what light was, only how it behaved. As long as rays and particles delivered reliable results, there was little incentive to question them too deeply. Despite this apparent stability, certain phenomena quietly challenged early assumptions. The appearance of colored fringes near shadows, later understood as diffraction, hinted that light did not always respect sharp geometric boundaries. The spreading of light through narrow openings suggested behavior that was difficult to reconcile with simple straight-line motion. These effects were often noted but not fully integrated into dominant theories. Interference patterns, where light seemed to cancel itself out or reinforce itself, were even more troubling. If light consisted of particles, how could two streams of particles combine to produce darkness? Classical thinkers struggled with such questions, often setting them aside or proposing ad hoc explanations. The core belief in rays and particles remained intact, but cracks were becoming visible. Still, it is important to recognize how resilient these early models were. They adapted by absorbing new observations without fundamentally changing their assumptions. When light spread, it was said that particles scattered. When patterns appeared, forces or interactions were invoked. These explanations were often vague, but they preserved the underlying framework. The authority of figures like Newton further solidified these views. His success in mechanics, gravity, and mathematics made his ideas enormously influential. Questioning his theory of light sometimes felt like questioning the foundations of science itself. As a result, alternative views struggled for acceptance, even when supported by evidence. Education also reinforced early models. Textbooks, lectures, and diagrams presented light as rays bouncing and bending through space. Generations of students learned to think of light in this way, embedding the concepts deeply into scientific culture. Once a model becomes a teaching tool, it gains a kind of permanence that goes beyond its original purpose. Philosophically, these models reflected a broader belief that nature was ultimately mechanical. Everything, including light, was expected to be explainable in terms of motion, contact, and force. This belief shaped not only optics but all of classical physics. Light was not special, it was part of a clockwork universe. Yet, this very success planted the seeds of future upheaval. By insisting that light fit into mechanical categories, classical physics limited its ability to respond when light behaved in non-mechanical ways. The more precisely scientists measured light, the more uncomfortable these limitations became. Before quantum theory, however, these tensions had not yet reached a breaking point. Light was still largely understood through the lens of rays and particles, supported by centuries of observation and application. These ideas were not naive guesses. They were sophisticated models that reflected the best thinking of their time. They also revealed something profound about human understanding. We interpret new phenomena using familiar concepts. Rays borrowed from geometry, particles from everyday experience with matter. These metaphors allowed scientists to think, calculate, and predict. Even when they fell short, they provided a foundation on which deeper theories could be built. In hindsight, it is tempting to see early ideas about light as stepping stones toward quantum theory. But they were more than that. They were complete worldviews in their own right, coherent systems that explained a vast range of phenomena. Their eventual limitations do not diminish their intellectual achievement. By the end of the classical era, light was understood as something that traveled, interacted, and obeyed laws. Whether imagined as rays or particles, it was no longer mysterious or magical. It was a subject of measurement, calculation, and control. This transformation from myth to mechanism was one of the great achievements of pre-quantum science. Yet, beneath this confidence lay unanswered questions. These questions would eventually force scientists to abandon purely classical thinking and embrace a radically new understanding. But that moment had not yet arrived. For now, light remained firmly anchored in the familiar language of rays and particles, illuminating the world while quietly preparing to challenge everything humans thought they knew about nature. Long before quantum theory transformed physics, the wave idea of light emerged as one of the most serious alternatives to particle-based explanations. This shift did not happen suddenly, nor was it driven by a single experiment. It developed slowly through observation analogy, and the growing realization that some behaviors of light were difficult to reconcile with straight-line particles alone. The classical wave theory of light represented a profound change in how scientists imagined the invisible processes underlying vision and illumination. The concept of waves was already familiar to early scientists through sound and water. Sound waves moved through air, spreading outward from a source, bending around obstacles, and overlapping with one another. Water waves rippled across surfaces, creating patterns of interference and motion that could be easily observed. These everyday experiences made waves an attractive model for explaining phenomena that particles struggled to describe. Light, though far faster and more elusive, began to be considered within this same conceptual framework. Christian Huygens played a central role in formalizing the wave theory of light in the late 17th century. He proposed that light propagated as a wave through space, spreading outward from a source in all directions. According to his principle, every point on a wavefront could be treated as a source of new secondary waves. The combined effect of these waves determined how light advanced through space. This idea allowed light to bend, spread, and interfere in ways that particle theories could not naturally explain. Huygens' approach provided a powerful explanation for reflection and refraction. When a wave encountered a surface, it reflected according to geometric rules that matched observation. When it entered a new medium, such as glass or water, its speed changed, causing the wavefront to bend. This bending, or refraction, followed predictable laws that matched experimental results. Unlike Newton's particle theory, which required attractive forces to pull particles into denser media, the wave model explained refraction as a natural consequence of changing wave speed. Despite its elegance, the wave theory initially struggled to gain acceptance. One major obstacle was the apparent straight-line motion of light. Waves, as people understood them, tended to spread out and diffract around obstacles. Light, by contrast, cast sharp shadows and seemed to travel in straight lines unless deliberately manipulated. This apparent contradiction made many scientists hesitant to abandon particle models. To resolve this, wave theorists argued that light waves had extremely small wavelengths. Because of this, their spreading was usually too subtle to notice in everyday situations. Only under special conditions, such as narrow openings or fine edges, would wave effects become visible. At the time, this explanation was speculative, but it allowed the wave theory to coexist with ordinary optical observations. Another challenge was the question of what exactly was waving. Waves, as classically understood, required a medium. Water waves needed water, sound waves needed air or solids, and mechanical vibrations needed material support. If light was a wave, it too must travel through something. This assumption led to the introduction of the luminiferous ether, a hypothetical substance believed to fill all of space. The ether was imagined as an invisible, weightless medium permeating the universe. It was assumed to exist everywhere, even in regions of apparent emptiness, such as the space between planets and stars. Without the ether, classical physics could not easily explain how light waves traveled through a vacuum. The ether was not considered optional, It was a necessity within the wave framework. Designing the ether posed serious conceptual challenges. It had to be extremely rigid to support the enormous speed of light, far greater than that of sound. At the same time, it had to be so subtle that it offered no resistance to the motion of planets and other celestial bodies moving through space. It could not be dragged along by matter, nor could it slow objects down. These requirements made the ether unlike any known material, yet it was widely accepted because it solved an otherwise fatal problem for wave theory. Throughout the 18th century, the wave theory of light remained a minority view, overshadowed by Newton's influence. However, the situation began to change in the early 19th century with the work of Thomas Young. Young conducted experiments that revealed interference patterns when light passed through closely spaced openings. These patterns of bright and dark fringes could not be explained by particles alone. They strongly suggested that light waves could reinforce or cancel each other, just like water or sound waves. Young's experiments marked a turning point. They provided clear evidence that light exhibited wave-like behavior under certain conditions. Darkness appearing where light should have been present was particularly troubling for particle theories. In the wave model, however, this phenomenon followed naturally from destructive interference, where wave peaks and troughs canceled out. Further support came from Augustin John Fresnel, who developed a more detailed mathematical framework for wave optics. Fresnel showed that diffraction and interference effects could be precisely predicted using wave equations. His work demonstrated that wave theory was not just qualitatively appealing but quantitatively powerful. Patterns observed in experiments matched mathematical predictions with remarkable accuracy. Polarization presented another major triumph for wave theory. Light could be polarized, meaning its vibrations could be restricted to certain directions. This behavior strongly suggested that light waves were transverse, vibrating perpendicular to their direction of travel. Particle theories struggled to account for polarization, while wave theory embraced it naturally. However, transverse waves introduced a new complication for the ether. Transverse waves require a medium with shear rigidity, like a solid. Fluids cannot support such waves. This implied that the ether behaved like a solid in some respects, despite being completely invisible and offering no resistance to motion. The ether thus became an increasingly strange entity, possessing properties tailored precisely to fit theoretical needs. As wave theory gained ground, the ether became deeply embedded in scientific thinking. It was not seen as speculative or exotic, but as a natural extension of known physics. Textbooks described it as calmly as air or water, and scientists debated its properties with confidence. The ether provided a conceptual anchor for understanding light as a mechanical wave phenomenon. The wave theory also reshaped how scientists thought about color. Instead of being caused by different particle types, color was associated with different wavelengths. Shorter wavelengths corresponded to one color, longer wavelengths to another. This explanation unified color, interference, and diffraction under a single framework, strengthening the appeal of the wave model. Yet, even as wave theory triumphed in optics, unease remained beneath the surface. The ether, while mathematically useful, resisted direct detection. Numerous experiments attempted to measure Earth's motion through the ether, assuming that such motion should affect the speed of light in different directions. Early attempts produced ambiguous or contradictory results, but they did not immediately undermine belief in the ether. The wave theory of light before quantum mechanics was thus both a success and a source of tension. It explained phenomena that particles could not, unified diverse observations, and provided a powerful mathematical framework. At the same time, it relied on an unseen medium with increasingly implausible properties. This contradiction was tolerated because no better alternative existed. Importantly, wave theory changed the language of physics. Light was no longer imagined as tiny objects flying through space, but as a continuous disturbance, spreading smoothly and interacting with itself. Energy was distributed across wavefronts rather than concentrated in discrete entities. This continuity became a defining feature of classical physics and shaped expectations about how nature should behave. By the mid-19th century, wave theory had become the dominant explanation of light. Particle ideas did not disappear, but they were largely sidelined. The ether was accepted as a real component of the universe, even if it could not be touched or seen. Light, in this classical view, was a vibration of this all-pervading medium, carrying energy and information across vast distances. This perspective laid the groundwork for later developments, including electromagnetic theory. It also set the stage for future crises. The more successful wave theory became, the more troubling the ether's invisibility grew. Classical physics had committed itself to a medium that no experiment could clearly reveal. Before quantum theory, however, these issues remained unresolved. The wave theory of light, supported by interference, diffraction, and polarization, represented one of the great achievements of classical science. It demonstrated the power of analogy, mathematics, an experiment to uncover hidden structures in nature. At the same time, it revealed the limits of classical thinking, limits that would only become fully apparent in the decades to come. As the wave theory of light became more refined, it began to influence how scientists understood not just optics, but the structure of physical explanation itself. Light waves were seen as continuous, smooth, and governed by precise mathematical laws. This view fit perfectly with the broader classical belief that nature was fundamentally continuous rather than discrete. Energy flowed smoothly, motion changed gradually, and nothing happened in sudden jumps. This assumption would later become one of the deepest points of conflict with quantum theory, but before that, it was considered almost self-evident. The success of wave theory encouraged physicists to search for deeper unification. If light was a wave, and if waves required a medium, then that medium must be a fundamental component of reality. The ether was no longer just a convenient hypothesis, it became a central element of the classical worldview. Space itself was no longer empty. It was filled with a substance that carried vibrations, transmitted forces, and connected distant objects through continuous fields. This idea subtly changed how scientists thought about emptiness. What appeared to be a vacuum was, in fact, a dynamic environment capable of supporting motion and energy transfer. The ether was imagined as perfectly transparent, undetectable by ordinary means, yet absolutely real. It was not a philosophical abstraction, but a physical necessity within classical wave theory. As experimental techniques improved, physicists began to study light with increasing precision. Measurements of reflection, refraction, and diffraction became more accurate, and wave theory continued to match observations impressively well. Mathematical descriptions grew more sophisticated, allowing scientists to predict complex interference patterns and subtle optical effects. This predictive power reinforced confidence in the wave model and pushed particle explanations further into the background. One of the most important developments during this period was the realization that wave behavior could explain limits to optical resolution. No matter how perfect a lens was, there was a fundamental limit to how finely it could focus light. This limit arose not from imperfections in glass or craftsmanship, but from the wave nature of light itself. When waves passed through an aperture, they spread slightly, blurring fine details. This insight was deeply satisfying because it showed that apparent technological limits were actually rooted in fundamental physical laws. The wave picture also reshaped ideas about intensity and brightness. Instead of thinking in terms of more or fewer particles, brightness was associated with wave amplitude. A brighter light corresponded to a wave with greater oscillation strength. Energy was spread continuously across the wave, not concentrated in individual entities. This view aligned naturally with classical energy conservation and thermodynamics. As these ideas matured, wave theory became deeply embedded in education and scientific culture. Students learned to visualize light as rippling wavefronts advancing through space. Diagrams showed crests and troughs, interference fringes, and diffraction patterns. These images shaped intuition and influenced how new problems were approached. Once a way of thinking becomes intuitive, it gains enormous staying power. At the same time, unresolved questions about the ether grew more troubling. Experiments designed to detect Earth's motion through the ether became increasingly sensitive. If the ether filled all of space, then Earth's movement around the Sun should produce measurable changes in the speed of light, depending on direction. Repeated attempts were made to observe such effects, but the results stubbornly refused to match expectations. Rather than abandoning the ether, physicists initially modified its properties. They suggested that matter might partially drag the ether along, or that length and time measurements were subtly affected by motion through it. These adjustments preserved the ether while complicating its description. Each modification solved one problem while creating another, but the overall framework remained intact. This willingness to preserve the wave-ether picture at almost any cost reveals how deeply it was trusted. The wave theory of light was not just an explanation, it was a foundation upon which much of classical physics rested. Abandoning it would have meant questioning the continuity of nature, the mechanical interpretation of waves, and the very meaning of physical explanation. The wave view also influenced how scientists thought about causality. Changes in a light source propagated outward through the ether, affecting distant objects only after a finite time. This reinforced the idea that causes and effects were linked through continuous processes, not instantaneous action at a distance. Light waves carried information step by step through space, preserving a sense of local interaction that many physicists found philosophically comforting. Yet, even as wave theory dominated optics, subtle anomalies continued to accumulate. Certain interactions between light and matter did not fit easily into the wave picture. For example, when light struck certain materials, electrons were ejected in ways that depended on light frequency rather than intensity. Classical wave theory predicted that increasing brightness should increase energy transfer, but experiments did not always agree. Initially, these effects were seen as minor puzzles rather than serious threats. The classical wave view also struggled with explaining why light sometimes behaved as if its energy were localized. Waves spread energy over large regions, yet light could produce sharply defined effects, such as precise chemical reactions or localized heating. These contradictions were not yet fully appreciated, but they hinted that continuity might not tell the whole story. Despite these issues, wave theory before quantum mechanics represented an extraordinary intellectual achievement. It unified optics under a single conceptual framework, connected light to other wave phenomena, and demonstrated the power of mathematics to describe invisible processes. It showed that human beings could infer the structure of reality from patterns of observation, even when the underlying medium could not be directly seen. The ether, for all its problems, symbolized this confidence. It was a reminder that science often posits entities, not because they are directly observable, but because they make sense of what is observed. In this respect, the ether was no stranger than atoms once were. Its eventual rejection does not make belief in it foolish, it reflects the evolving nature of scientific understanding. Before quantum theory, light as a wave traveling through the ether was one of the most coherent pictures of nature ever constructed. It explained how light spread, how it bent, how it interfered with itself, and how it could be manipulated by human-made devices. It fit neatly into a universe governed by continuous laws and mechanical processes. This picture also shaped expectations about what future discoveries should look like. Physicists expected deeper theories to refine the wave model, not overturn it. They believed that any remaining puzzles would be resolved by better understanding the ether or improving experimental precision. The idea that light might be fundamentally discrete, or that energy might come in indivisible packets, lay far outside mainstream thinking. In retrospect, this makes the later emergence of quantum theory all the more dramatic. The wave theory of light did not fail because it was careless or weak, but because it was too successful within its own assumptions. It described a continuous world so convincingly that the possibility of discontinuity seemed almost unthinkable. Understanding this pre-quantum wave view of light is essential for appreciating the shock that quantum ideas produced. It reveals that scientific revolutions do not arise from ignorance, but from the limits of even the best theories. Before quantum theory, light as a wave in the ether represented the height of classical understanding, a vision of nature as smooth, connected, and intelligible. Only when experiments forced physicists to confront phenomena that could not be absorbed into this picture did the need for a radically new framework become unavoidable. Before quantum theory, reflection and refraction were not mysterious or abstract phenomena. They were among the most concrete, visible, and mathematically controlled aspects of light. Long before scientists argued about whether light was a wave or a particle, they knew how it behaved when it struck surfaces, passed through transparent materials, or changed direction. These behaviors formed the backbone of classical optics and shaped how light was understood for centuries. Reflection was one of the earliest optical phenomena to be studied systematically. From polished metal mirrors in ancient civilizations to glass mirrors in later periods, people observed that light bounced off surfaces in a highly regular way. An object placed in front of a mirror appeared behind it, at a distance that seemed equal to the object's distance in front. This symmetry suggested that light followed strict geometric rules. Ancient Greek thinkers were already aware that the angle at which light strikes a mirror determines the angle at which it reflects. Over time, this observation was formalized into what became known as the law of reflection. The angle of incidence equals the angle of reflection. This rule did not depend on the material of the mirror or the color of the light. It worked universally, reinforcing the idea that light's behavior could be captured by simple geometry. What made reflection so powerful as a concept was its predictability. By drawing straight lines representing light rays, one could determine exactly where an image would appear. This geometric approach did not require any assumptions about the internal nature of light. Whether light was imagined as particles, waves, or something else entirely, its reflection could be described using the same rules. This universality made reflection a cornerstone of optical science. Refraction, the bending of light as it passes from one medium into another, added a layer of complexity. When light moved from air into water or glass, it changed direction. Objects submerged in water appeared displaced, bent, or distorted. These effects fascinated observers for centuries and raised deeper questions about why light behaved this way. The systematic study of refraction advanced significantly during the medieval and early modern periods. Scholars measured how much light bent when entering different materials and discovered consistent patterns. Eventually, this behavior was captured mathematically in what became known as Snell's law. This law related the angles of incidence and refraction to the properties of the two media involved. Like the law of reflection, it applied broadly and reliably. Geometric optics treated both reflection and refraction using the same basic assumption. Light travels in straight lines until something forces it to change direction. These straight lines, called rays, were abstract representations of light's path. They were not physical objects but conceptual tools that allowed scientists to predict outcomes with precision. This ray-based approach was incredibly successful. It explained why lenses focus light, how prisms spread light into colors, and how images form in mirrors and optical instruments. By tracing rays through systems of surfaces, scientists could design devices that manipulated light in precise ways. Telescopes, microscopes, cameras, and eyeglasses all depended on these principles. One of the most striking features of geometric optics was its independence from deeper theories. Reflection and refraction could be understood and applied without knowing whether light was a wave or a particle. This made geometric optics robust and widely usable. Engineers, artisans, and scientists could work effectively with light using geometry alone. However, this strength also limited deeper inquiry. Because geometric optics worked so well, it discouraged questions about what light actually was. As long as rays could be drawn and predictions made, the underlying nature of light seemed less urgent. This pragmatic attitude shaped pre-quantum understanding and delayed the recognition of deeper inconsistencies. Reflection was often explained mechanically within particle theories. Light particles were imagined to bounce off surfaces like balls striking a wall. This analogy fit the observed law of reflection neatly and reinforced the particle view. Smooth surfaces produced regular reflection, while rough surfaces scattered particles in many directions, explaining diffuse reflection. Refraction, in particle models, required additional assumptions. Newton proposed that particles of light experienced forces at the boundary between media. When entering a denser medium, particles were pulled toward the surface, changing their direction. While this explanation matched observed bending, it relied on hypothetical forces that could not be directly tested. Wave theories offered alternative explanations. In wave models, reflection occurred when waves bounced back from a boundary, while refraction occurred because wave speed changed in different materials. When part of a wave entered a slower medium, its direction shifted, producing bending. This explanation avoided mysterious forces and tied refraction to measurable properties like wave speed. Despite these competing interpretations, geometric optics remained neutral. It described what happened without committing to why it happened. This neutrality allowed reflection and refraction laws to survive intact even as theories about light's nature evolved. The success of geometric optics also shaped expectations about scientific explanation. It reinforced the belief that nature was orderly and mathematically precise. Light did not behave randomly. It followed exact rules that could be expressed in simple equations. This confidence in determinism became a hallmark of classical physics. Artists and architects also relied on these principles. The development of linear perspective during the Renaissance was deeply connected to ray optics. Painters used geometric rules to represent three-dimensional space on flat surfaces, assuming that light traveled in straight lines from objects to the eye. This artistic success further reinforced the ray model as intuitively true. In astronomy, reflection and refraction played crucial roles. Telescopes used mirrors or lenses to gather and focus light from distant stars. Understanding how light reflected off curved mirrors or refracted through lenses was essential for improving image clarity and magnification. The ability to predict and correct optical aberrations depended entirely on geometric optics. Refraction also revealed that different colors of light bent by different amounts. When white light passed through a prism, it spread into a spectrum. This dispersion was initially explained geometrically by assigning different refractive properties to different rays. Although this raised questions about the nature of color, it did not challenge the basic ray framework. The limitations of geometric optics became apparent only under certain conditions. When light passed through very narrow openings or encountered very small obstacles, it behaved in ways that rays could not easily explain. Instead of sharp boundaries, blurred patterns and fringes appeared. These effects were later understood as diffraction and interference, but for a long time they were treated as anomalies or secondary effects. Before quantum theory, these anomalies did not undermine the core principles of reflection and refraction. Instead, they were often attributed to imperfections or special cases. The main body of optical science continued to rely on geometric descriptions because they worked in most practical situations. Geometric optics also shaped how scientists thought about causality and locality. Light traveled from source to object to eye along specific paths. Each interaction occurred at a definite place and time. This reinforced a classical view of the universe as a network of local interactions governed by clear rules. The emphasis on straight-line propagation also influenced assumptions about speed. Light was assumed to move extremely fast, but at a finite rate. This allowed for time delays and sequential causation. Even before precise measurements of light's speed, its finite propagation was consistent with ray-based thinking. Importantly, reflection and refraction laws did not emerge from abstract theory alone. They were grounded in careful observation and measurement. This empirical foundation gave them a level of certainty that speculative ideas about light's substance lacked. As a result, they became some of the most trusted principles in physics. Before quantum theory, the study of light through reflection, refraction, and geometry represented the height of classical clarity. Light could be controlled, predicted, and harnessed using straightforward rules. These rules did not require exotic assumptions or hidden entities. They made light feel understandable and manageable. Yet, this clarity came at a cost. By focusing on paths rather than processes, geometric optics sidestepped deeper questions. Why did light always choose the path it did? What determined how much it bent? Why did it sometimes refuse to behave like a simple ray? These questions lingered beneath the surface. Still, the achievements of classical reflection and refraction should not be underestimated. They transformed light from a mysterious phenomenon into a tool of precision. They enabled technological revolutions in science, navigation, medicine, and art. They demonstrated that nature could be described with mathematical elegance. Before quantum theory, this was enough. Light, as understood through reflection, refraction, and geometric optics, fit comfortably into a deterministic, orderly universe. It behaved as expected, followed rules, and responded predictably to human intervention. Only later would deeper experiments reveal that beneath these clean geometric laws lay a more complex and surprising reality. As reflection and refraction became firmly established through geometric optics, they began to shape not only scientific practice, but also the deeper assumptions scientists held about how nature operates. Light, in this framework, appeared obedient to geometry, as if space itself dictated its behavior. Wherever surfaces met, wherever materials changed, light responded instantly and precisely, adjusting its path according to fixed rules. This reliability created a sense that light was fundamentally simple, even if its underlying substance remained unknown. One of the most influential ideas emerging from geometric optics was that light always followed a well-defined path. Every ray had a history and a future. It originated from a source, interacted with surfaces or materials along the way, and eventually reached an observer or detector. Nothing about this process seemed ambiguous. If the initial conditions were known, the final outcome could be predicted exactly. This reinforced the classical belief that the universe was fully deterministic. This deterministic view had profound consequences. It encouraged scientists to believe that uncertainty was merely a sign of incomplete knowledge, not a fundamental feature of nature. If an image was blurry or distorted, the cause was assumed to be imperfect lenses, rough surfaces, or measurement error. The behavior of light itself was not questioned. It was assumed to be exact, lawful, and ultimately transparent to human understanding. Reflection, in particular, became a model for how physical laws should look. The law of reflection was simple, universal, and elegant. It did not depend on complicated conditions or hidden variables. It applied equally to sunlight, candlelight, and starlight. This universality made it feel almost self-evident, as if it could not possibly be otherwise. Such laws strengthened confidence in the idea that nature was governed by clear, mathematical principles waiting to be discovered. Refraction, though more complex, still fit within this worldview. Snell's law connected angles to material properties in a precise mathematical relationship. Once the refractive index of a material was known, the path of light could be calculated exactly. This suggested that materials possessed intrinsic optical properties that determined how they interacted with light. These properties were treated as stable and measurable, reinforcing the objectivity of classical physics. The success of lenses provided some of the strongest evidence for the power of geometric optics. By carefully shaping glass, humans learned to bend light to their will. Convex lenses could focus rays to a point, magnifying distant or tiny objects. Concave lenses could spread rays apart, correcting vision defects. These effects were not accidental. They followed directly from the laws of refraction. This gave people a sense of mastery over light, turning an abstract phenomenon into a controllable resource. This mastery extended into astronomy. Telescopes allowed light from distant stars and galaxies to be collected, redirected, and focused onto the human eye. The fact that light could travel across vast cosmic distances and still obey the same reflection and refraction laws reinforced the idea that these principles were truly universal. The same geometry applied on Earth and in the heavens, uniting terrestrial and celestial physics. Geometric optics also influenced how scientists thought about time. Because light was assumed to follow a path, it was natural to imagine it moving along that path at a definite speed. Even before precise measurements of light's velocity, it was treated as finite. This allowed scientists to think of light as carrying information from one place to another over time, preserving the classical link between cause and effect. The ray model also shaped ideas about observation itself. Vision was understood as light rays traveling from objects into the eye. The eye became an optical instrument, governed by the same rules as cameras and telescopes. This mechanistic view of perception blurred the boundary between observer and instrument, reinforcing the belief that observation was a passive process of receiving information rather than an active interaction. Despite its strengths, geometric optics quietly excluded certain phenomena from serious consideration. Effects like diffraction and interference did not fit neatly into a ray-based description. When light spread into regions where rays predicted darkness, or when patterns of alternating brightness appeared, these effects were often treated as secondary complications. They were acknowledged but not emphasized, especially in practical applications. This selective focus shaped scientific priorities. Research and education emphasized situations where geometric optics worked best. Large-scale systems, smooth surfaces, and well-defined beams. Situations where it failed were often labeled as special cases. This reinforced the impression that rays represented the true nature of light, while deviations were exceptions rather than clues to deeper principles. The conceptual separation between rays and physical reality also played a role. Because rays were understood as abstractions, scientists could avoid confronting contradictions directly. If light behaved strangely, one could argue that the ray model was only an approximation, without questioning the underlying assumptions about determinism and locality. This flexibility allowed geometric optics to coexist with emerging wave theories for a long time. In engineering and technology, this coexistence was particularly evident. Designers used ray tracing to build optical systems even as wave theorists explored interference and diffraction. The two approaches addressed different scales and problems. Rays handled large-scale geometry, while waves addressed fine details. This division of labor was productive, but also masked deeper tensions. Another important consequence of reflection and refraction laws was the belief that light chose its path according to fixed rules rather than probabilistic ones. When light reflected from a mirror, it did not sometimes reflect at one angle and sometimes at another. It always obeyed the same law. This consistency made it difficult to imagine a world in which light's behavior could be inherently uncertain. This mindset would later clash dramatically with quantum ideas, but before that, it was reinforced at every turn. The cleaner and more precise optical laws became, the stronger the conviction grew that nature itself was precise and exact at all levels. The cultural impact of geometric optics should not be underestimated. The ability to predict how light would behave contributed to a broader Enlightenment belief in reason, order, and progress. If light, one of the most elusive elements of nature, could be understood geometrically, then perhaps everything could. Optics became a symbol of humanity's capacity to uncover nature's secrets through mathematics. Yet, the very success of this approach created blind spots. By focusing on paths rather than processes, classical optics avoided questions about how light interacted with matter at a deeper level. Reflection was described as bouncing, refraction as bending, but the mechanisms behind these behaviors remained largely unexplored. Forces were invoked, speeds were adjusted, but no microscopic explanation was fully convincing. As experiments became more precise in the late classical period, these gaps became harder to ignore. Light interacting with very small structures, very short timescales, or very low intensities began to reveal behaviors that did not scale smoothly from geometric predictions. Still, these were often seen as technical challenges rather than fundamental problems. Before quantum theory, reflection and refraction represented the triumph of description over explanation. Scientists could say with confidence what light would do, even if they could not fully say why. This distinction mattered less in a classical worldview that valued predictability above all else. In hindsight, the emphasis on geometry was both a strength and a limitation. It allowed rapid progress and technological innovation, but it also delayed the recognition that light's behavior could not be fully captured by paths and angles alone. The universe was more subtle than straight lines suggested. Nevertheless, the legacy of geometric optics remains profound. Even today, reflection and refraction laws are used daily in science and engineering. They survived the quantum revolution not because they were replaced, but because they were revealed as approximations within a deeper framework. Before quantum theory, however, they were not approximations. They were seen as fundamental truths about how light worked. They fit perfectly into a classical universe that was orderly, continuous, and predictable. Light followed rules, geometry ruled those rules, and human reason could master them. This confidence would eventually be shaken, but only after centuries of success. Reflection and refraction were not stepping stones casually discarded. They were pillars of classical understanding. To appreciate the shock of later discoveries, one must first understand how complete and convincing this geometric picture of light once seemed. Before quantum theory, interference, diffraction, and polarization represented some of the most intriguing and unsettling behaviors of light. Unlike reflection and refraction, which fit neatly into geometric rules, these phenomena hinted that light was capable of interacting with itself, spreading into unexpected regions, and exhibiting directional properties that challenged simple ray or particle explanations. Together, they played a crucial role in reshaping classical understanding and strengthening the wave theory of light. Interference was one of the most striking discoveries. It revealed that light could combine with itself in ways that produced both brightness and darkness. When two beams of light overlapped, they did not simply add together. Instead, under certain conditions, they created patterns of alternating bright and dark regions. This behavior was famously demonstrated when light passed through two closely spaced openings and formed a series of fringes on a screen. The appearance of darkness where light was expected was particularly troubling for particle-based views. If light were made of particles, overlapping streams should only increase brightness, never cancel it out. In the wave interpretation, however, interference followed naturally. Waves could reinforce each other when their peaks aligned or cancel each other when peaks met troughs. Interference thus provided strong evidence that light behaved as a wave, at least in certain situations. Diffraction revealed another wave-like aspect of light. When light encountered a narrow opening, a sharp edge, or a small obstacle, it did not always travel in straight lines as geometric optics predicted. Instead, it spread out into regions that should have remained dark if light were strictly confined to rays. This spreading produced characteristic patterns of brightness and shadow that depended on the size of the opening and the wavelength of the light. Diffraction showed that light was sensitive to boundaries and constraints, responding in a smooth, continuous way rather than following rigid paths. The smaller the opening, the more pronounced the spreading became, reinforcing the idea that light had an intrinsic scale associated with its behavior. These diffraction effects were subtle in everyday life, which is why they were not noticed earlier. Most objects and openings are large compared to the wavelength of visible light, so light usually appears to travel in straight lines. Only when experiments were carefully designed did diffraction become visible. This explained why geometric optics worked so well in practical situations while still being fundamentally incomplete. Diffraction exposed the limits of ray-based descriptions and showed that straight-line propagation was an approximation rather than an absolute rule. Polarization added yet another layer of complexity. It revealed that light waves had a specific orientation. Ordinary light vibrated in many directions perpendicular to its direction of travel. Under certain conditions, however, light could be constrained to vibrate in a single plane. This polarized light behaved differently when reflected, refracted, or passed through special materials. Polarization effects could not be easily explained by particle models which lacked a clear concept of directional vibration. In wave theory, polarization made sense only if light waves were transverse, meaning their oscillations occurred perpendicular to their direction of motion. The discovery of polarization was especially important because it ruled out certain types of wave models. Longitudinal waves, like sound waves, vibrate in the same direction as they travel and cannot be polarized. The fact that light could be polarized meant it had to be a transverse wave. This insight placed strong constraints on theories of light and had deep implications for the nature of the medium through which light propagated. It implied that the ether had to support transverse vibrations, a property associated with solids rather than fluids, making the ether concept increasingly strained. Together, interference, diffraction, and polarization painted a picture of light as a phenomenon that could not be fully captured by simple trajectories or collisions. Light could overlap with itself, spread beyond expected boundaries, and exhibit directional structure. These behaviors emphasized continuity rather than discreteness, supporting the classical wave view and reinforcing the belief that light energy was distributed smoothly through space. At the same time, these phenomena were carefully integrated into classical physics without immediately overturning existing frameworks. They were treated as special cases that emerged under specific conditions, rather than as evidence that all light behaved in fundamentally different ways. This allowed wave optics to coexist with geometric optics. Rays remained useful for large-scale predictions, while waves were invoked to explain fine details and subtle effects. The mathematical treatment of these phenomena further strengthened confidence in classical wave theory. Interference and diffraction patterns could be predicted with remarkable accuracy using wave equations. Polarization effects could be described using vector models of oscillation. The success of these calculations suggested that light's behavior, however complex, was still governed by precise laws. This reinforced the classical conviction that nature was deterministic and mathematically ordered. Yet, beneath this success lay unresolved questions. If light was a continuous wave, how did it transfer energy to matter in discrete, localized ways? How could a spread-out wave produce sharp chemical or electrical effects? These questions were not yet fully appreciated, but the phenomena of interference, diffraction, and polarization quietly pointed toward deeper mysteries. Before quantum theory, these effects represented both triumph and tension. They showcased the explanatory power of wave models while simultaneously exposing the limitations of classical intuition. They revealed that light was more subtle than straight lines and bouncing particles suggested, capable of behaviors that challenged everyday experience. In the classical era, interference, diffraction, and polarization were seen as advanced topics, explored in laboratories and textbooks rather than daily life. They marked the frontier of optical science, where the limits of existing ideas became visible. They did not yet demand a complete overhaul of physics, but they made it clear that light could not be understood through geometry alone. These phenomena prepared the ground for future revolutions. By demonstrating that light could behave as a wave in profound and measurable ways, they set expectations that would later collide with experiments showing particle-like behavior. Before quantum theory, however, interference, diffraction, and polarization stood as powerful evidence that light was a continuous, wave-like entity, spreading smoothly through space and obeying elegant mathematical laws. even as it quietly hinted that the classical story was not yet complete. Before quantum theory, Maxwell's electromagnetic theory represented the most complete and ambitious explanation of light ever achieved within classical physics. It did not merely describe how light behaved at surfaces or through openings. It explained what light was in terms of fundamental forces. By uniting electricity, magnetism, and optics into a single framework, Maxwell transformed light from a mysterious optical phenomenon into a central feature of the physical universe. In the early 19th century, electricity and magnetism were studied as separate phenomena. Electrical charges produced forces, sparks, and currents, while magnets exerted attraction and repulsion and influenced compass needles. Through careful experiments, scientists began to notice deep connections between these effects. Electric currents could create magnetic fields, and changing magnetic fields could induce electric currents. These discoveries suggested that electricity and magnetism were not independent, but different aspects of a single underlying interaction. James Clerk Maxwell took these experimental insights and expressed them in a set of mathematical equations that described how electric and magnetic fields evolve and interact. His equations showed that a changing electric field generates a magnetic field, and a changing magnetic field generates an electric field. This mutual generation meant that electric and magnetic disturbances could sustain each other, propagating through space as waves. When Maxwell calculated the speed of these electromagnetic waves using known electrical and magnetic constants, he found something extraordinary. The predicted speed matched the measured speed of light. From this, Maxwell concluded that light itself was an electromagnetic wave. Visible light was simply one small part of a vast spectrum of electromagnetic radiation, differing only in wavelength and frequency. This insight was revolutionary. It meant that light no longer needed a special, separate explanation. It was governed by the same laws that described electrical sparks and magnetic forces. Optics was no longer an isolated branch of physics, but part of a unified theory of fields. Maxwell's theory described light as a transverse wave composed of oscillating electric and magnetic fields, perpendicular to each other and to the direction of propagation. These fields were not vibrations of material particles, but entities in their own right, capable of existing and evolving in space. This marked a significant shift in thinking. Physical reality was no longer defined solely by matter and motion, but also by fields. The theory explained many optical phenomena with remarkable elegance. Reflection and refraction could be understood in terms of how electromagnetic waves interacted with charged particles in materials. Polarization followed naturally from the transverse nature of the fields. Interference and diffraction arose from the superposition of waves. All of these behaviors emerged from a single set of equations, rather than from separate rules. Maxwell's theory also predicted phenomena that had not yet been observed. It implied the existence of electromagnetic waves beyond the visible spectrum. Later experiments confirmed radio waves, infrared radiation, ultraviolet light, X-rays, and gamma rays, all as manifestations of the same underlying phenomenon. This predictive power greatly strengthened confidence in the theory. Despite its success, Maxwell's theory still relied on the concept of the ether. Electromagnetic waves, like all classical waves, were assumed to require a medium through which to propagate. The electric and magnetic fields were thought to represent stresses and motions within this ether. Although Maxwell himself was cautious about specifying the ether's mechanical properties, most physicists accepted its existence as necessary. This acceptance reflected the classical commitment to continuity. Fields varied smoothly in space and time, and energy flowed continuously through them. Light was not emitted or absorbed in discrete chunks, but spread out as a wave, distributing energy across expanding wavefronts. This view aligned perfectly with classical mechanics and thermodynamics. Maxwell's theory also reinforced the idea that physical laws were local. Changes in a field at one point influenced neighboring points, and effects propagated outward at a finite speed. There was no instantaneous action at a distance. Light carried energy and information through space step by step, preserving causality and locality. The mathematical nature of the theory had a profound impact on physics. Maxwell's equations were elegant, compact, and deeply symmetrical. They suggested that nature could be understood through abstract mathematical structures, even when those structures did not correspond directly to mechanical models. This encouraged a shift away from purely mechanical explanations toward field-based thinking. However, this abstraction also created discomfort. Fields were invisible and intangible. Unlike particles, they could not be grasped or visualized easily. Some physicists struggled to accept fields as real physical entities, rather than convenient mathematical tools. Nevertheless, the success of the theory gradually overcame these reservations. Before quantum theory, Maxwell's electromagnetic view of light was considered essentially complete. It explained known optical phenomena, unified major branches of physics, and made successful predictions. To many physicists at the end of the 19th century, it seemed that the nature of light had finally been fully understood. Yet, subtle problems remained. When Maxwell's theory was applied to thermal radiation, it led to predictions that conflicted with experiment. Classical electromagnetism suggested that objects should emit infinite energy at high frequencies, an obviously unphysical result. Additionally, interactions between light and matter sometimes showed behavior that could not be explained by continuous waves alone. These issues were initially seen as technical difficulties rather than signs of a fundamental breakdown. The core structure of Maxwell's theory was so successful that few imagined it would need radical revision. Instead, physicists expected that refinements in understanding matter or the ether would resolve the remaining discrepancies. In hindsight, Maxwell's theory represented both the pinnacle and the limit of classical thinking about light. It provided a coherent, unified, and mathematically precise description that shaped physics for decades. At the same time, its assumptions about continuity and energy distribution would eventually clash with experimental reality. Before quantum theory, however, Maxwell's electromagnetic theory stood as one of the greatest achievements in the history of science. It transformed light from an optical curiosity into a fundamental expression of the electromagnetic structure of the universe, illuminating not only the world around us but the deep connections underlying physical law itself. Before quantum theory, classical explanations of light achieved extraordinary success. They described a wide range of phenomena with precision, enabled transformative technologies, and unified major areas of physics. At the same time, they carried inherent limitations that gradually became impossible to ignore. The story of classical light is therefore not one of failure, but of a framework that worked beautifully within its domain while quietly revealing the boundaries of its own power. One of the greatest successes of classical theories was their ability to predict and control light's behavior in everyday and technological contexts. Reflection, refraction, interference, diffraction, and polarization could all be described using well-established principles. Engineers and scientists used these laws to design lenses, mirrors, telescopes, microscopes, cameras, and optical instruments with remarkable accuracy. Light could be bent, focused, split, and recombined according to precise calculations. This practical reliability made classical optics indispensable. Another major success was unification. With Maxwell's electromagnetic theory, light was no longer an isolated phenomenon. It became part of a broader framework that linked electricity, magnetism, and radiation. This unification explained why light traveled at a constant speed, why it exhibited wave-like properties, and how it interacted with charged matter. Few theories in physics have achieved such explanatory breadth. By the late 19th century, many physicists believed that the essential nature of light had been fully captured. Classical theories also reinforced a deterministic worldview. Light followed exact laws. Given a source and a set of conditions, its future behavior could be predicted with certainty. This determinism extended to energy flow, interference patterns, and electromagnetic interactions. Randomness played no fundamental role. Any uncertainty was attributed to experimental limitations or incomplete knowledge, not to nature itself. Despite these achievements, classical explanations struggled in specific but crucial areas. One limitation was their treatment of energy. In classical wave theory, energy was distributed continuously across a wave. This implied that light could deliver arbitrarily small amounts of energy to matter. However, experiments involving light interacting with atoms and electrons did not always behave this way. Certain effects occurred only when light exceeded a specific frequency, regardless of its intensity. Classical theory could not account for such thresholds. Thermal radiation posed another serious problem. Classical electromagnetism predicted that hot objects should emit increasing amounts of energy at higher frequencies, leading to an infinite total energy output. This result, known as the ultraviolet catastrophe, directly contradicted experimental observations. Attempts to fix the problem within classical physics failed. The theory's mathematical structure itself produced the contradiction. The interaction between light and matter revealed further weaknesses. Classical theories treated matter as collections of charged particles responding smoothly to electromagnetic waves. In reality, matter absorbed and emitted light in sharply defined ways. Spectral lines appeared at precise frequencies, not as continuous distributions. Classical physics could describe the propagation of light, but not its detailed exchange of energy with atoms. Another limitation lay in localization. Waves spread energy over space, yet light often produced highly localized effects. A photographic plate could darken at a specific point. A chemical reaction could be triggered in a precise region. Classical wave theory struggled to explain how a broadly distributed wave could produce such focused outcomes without invoking ad hoc assumptions. The ether, once seen as a strength, became a growing liability. Classical wave theories required a medium to support light waves, yet all attempts to detect this medium failed. Experiments designed to measure Earth's motion through the ether consistently produced null results. The ether's properties had to be continually adjusted to fit observations, making it increasingly implausible as a physical substance. Even Maxwell's field-based approach, while reducing reliance on mechanical ether models, did not fully eliminate the problem. Fields still seemed to require some underlying medium. The inability to reconcile the ether with experimental evidence undermined confidence in the classical picture. Even as its mathematical elegance remained unquestioned, there was also a conceptual limitation in how classical theories handled scale. They worked exceptionally well at human and astronomical scales but faltered at very small scales. As experiments probed microscopic systems, discrepancies multiplied. Classical models lacked a natural way to describe discrete structures and quantized behavior, which appeared increasingly important in atomic phenomena. Importantly, these limitations were not obvious at first. Classical theories worked so well in most situations that problematic cases were initially seen as anomalies. Physicists expected that refinements, not revolutions, would resolve them. This confidence delayed the recognition that something more radical was needed. The tension between success and failure created a paradoxical situation. On one hand, classical theories of light were among the most accurate and predictive frameworks ever developed. On the other, they produced results that were clearly unphysical when pushed beyond certain limits. The same equations that explained interference and polarization also predicted infinities and contradictions. This duality shaped the mindset of late 19th century physics. There was a sense that the major problems had been solved, coupled with unease about a few stubborn inconsistencies. Light, once thought fully understood, became a source of deep confusion. The limitations of classical explanations were not merely technical. They challenged fundamental assumptions about continuity, determinism, and the nature of energy. If classical ideas failed, it was not because of poor reasoning, but because the world itself did not conform entirely to classical expectations. Before quantum theory, these unresolved issues accumulated quietly. Each problem alone might have seemed manageable. Together, They formed a pattern that pointed toward the need for a new conceptual framework. Classical theories of light had reached their natural limits. Their success remains undeniable. They provided the foundation for modern technology, scientific instrumentation, and much of our understanding of electromagnetic phenomena. Even today, classical optics is used daily because it remains accurate within its domain. At the same time, their limitations are what made progress possible. By revealing where classical ideas broke down, they opened the door to a deeper understanding of nature. The transition to quantum theory did not erase classical light theory, it redefined its scope. Before quantum theory, light stood at the edge of human understanding. It was explained with extraordinary skill, yet it resisted complete capture. The successes of classical explanations illuminated the world, but their limitations illuminated something even more important: the path toward a new way of thinking about reality itself. Before quantum theory emerged, classical physics faced a growing collection of unresolved problems related to light. These problems did not appear suddenly, nor did they immediately overturn existing theories. Instead, they accumulated slowly, appearing as small cracks in an otherwise impressive structure. Over time, these cracks widened, revealing that the classical understanding of light, however successful, was incomplete. One of the earliest and most troubling issues involved how light interacted with matter at the microscopic level. Classical wave theory treated light as a continuous flow of energy spread smoothly across space. According to this view, increasing the intensity of light should increase the energy delivered to matter, regardless of the light's frequency. Experiments showed otherwise. In certain materials, electrons were emitted only when light exceeded a specific frequency, no matter how intense the light was. Below that frequency, no amount of brightness produced the effect. This behavior directly contradicted classical predictions. Another deep problem arose in the study of thermal radiation. When objects are heated, they emit light across a range of frequencies. Classical electromagnetic theory attempted to explain this emission by modeling matter as collections of oscillating charges. The resulting calculations predicted that energy output should increase without limit at higher frequencies. This implied that ordinary objects should radiate infinite energy, an obviously impossible result. Experimental measurements showed a clear peak in emission and a rapid drop off at high frequencies, something classical theory could not reproduce. Spectroscopy revealed further inconsistencies. When light from excited gases was analyzed, it displayed sharp spectral lines at precise frequencies rather than a continuous spread. Classical physics had no natural explanation for why atoms emitted or absorbed light only at specific frequencies. Attempts to model atomic motion using classical mechanics failed to account for these discrete patterns. The structure of matter itself seemed incompatible with continuous wave emission. Localization posed another conceptual challenge. Waves spread energy over wide regions, yet light often produced sharply localized effects. A photographic plate exposed to weak light would record distinct spots rather than a uniform blur. Chemical reactions triggered by light occurred at specific sites. Classical theory struggled to explain how a distributed wave could produce such concentrated outcomes without invoking arbitrary mechanisms. The ether problem also loomed large. Classical wave theories required a medium through which light propagated, yet repeated experiments failed to detect any evidence of such a medium. Attempts to measure Earth's motion through the ether consistently yielded null results. To preserve the ether concept, physicists proposed increasingly complex modifications, but each solution introduced new difficulties. The ether became an invisible, undetectable entity with properties unlike any known substance. Even Maxwell's field theory, while reducing dependence on mechanical ether models, did not fully escape this issue. Fields existed in space, but the nature of that space remained unclear. If space could support electromagnetic waves, what exactly was vibrating? The lack of a clear answer undermined confidence in the classical picture. There were also problems related to stability. Classical electromagnetism predicted that accelerating charges radiate energy. According to this principle, electrons orbiting atomic nuclei should continuously lose energy and spiral inward, causing atoms to collapse. Yet atoms were stable, matter existed. Classical theory offered no satisfactory explanation for this stability. Another unresolved issue concerned the speed of light. Classical physics assumed that velocities added in a straightforward way. If light traveled through a medium, its speed should vary depending on the motion of the observer relative to that medium. Experiments consistently showed that the speed of light was the same in all directions, regardless of Earth's motion. This result contradicted classical expectations and could not be explained without abandoning deeply held assumptions. These problems were not isolated. They appeared in different areas of physics, yet they all pointed toward the same conclusion. Classical ideas about continuity, determinism, and waves were insufficient. Light did not behave purely as a smooth, continuous entity when interacting with matter or at very small scales. Importantly, the scientific community did not immediately recognize the need for a radical change. Classical physics had been extraordinarily successful, and its failures seemed limited to specific edge cases. Many physicists believed that clever adjustments or new experimental insights would eventually resolve the discrepancies. However, as evidence accumulated, the pattern became impossible to ignore. Each unresolved problem challenged a different aspect of classical thinking. Energy could not be infinitely divisible. Matter did not respond smoothly to light. Space did not behave like a traditional medium. Determinism broke down at small scales. These issues created a growing sense of crisis at the turn of the 20th century. Light, once thought fully understood, became a source of profound uncertainty. The very phenomena that had inspired confidence in classical physics now revealed its limitations. The unresolved problems did more than expose gaps in existing theories. They forced physicists to question foundational assumptions. What if energy came in discrete units? What if light was neither purely a wave nor purely a particle? What if nature was not fully deterministic? The answers to these questions would reshape physics, but before quantum theory, they remained open, unsettling, and deeply puzzling. Classical explanations could describe how light traveled through space, but not how it exchanged energy with matter. They could predict interference patterns, but not atomic spectra. They could unify electricity and magnetism, but not reconcile theory with experiment in critical cases. In retrospect, these unresolved problems were not signs of failure, but of progress. They showed that science had reached the limits of a powerful framework. By pushing classical theories to their breaking point, physicists uncovered the need for a new way of thinking. Before quantum theory, light stood at the crossroads of understanding. It illuminated the world while simultaneously revealing the shadows in human knowledge. The unanswered questions surrounding light were not just technical puzzles, they were invitations to rethink the nature of reality itself.